Hello YouTube. Today I'm going to talk about the Maxwell equations and what in French we call ARQS for the approximation of quasi-stationary systems. So what it means is basically you have four equations given by Maxwell and his friends that are here on the left side of my screen. The first one says that all the electrostatic um, charges are around in space can be just summed and divided by epsilon 0. The second one tells us that the magnetic field has a conservative flow. Basically, if you take a ring and if there is a magnetic field that comes out here, it must come back on the other side. It's kind of complex, but it's a very useful law. Um, the third one tells us that electricity can be generated by a non-static, varying magnetic field B, and that the magnetic field is either caused by a current, so on the fourth one, so either these terms, okay, it's not big enough, red, okay, so either this term here stands for current, so if you put electricity, it will basically create a magnetic field. And the second one is this one. It just tells you that you can create magnetic field with varying electrostatic charges. Okay, so now I'm going to talk about the ARQS. Okay, so we suppose that the currents and the charges will will vary over time very slowly. So there is a conservation of the charges because we'll say that it doesn't change much. We have almost the same charges on our system, and then we can this works. Okay, I'm going to think. Okay, we usually say that this RQS works only for a few conditions. Um, if your system is consists into two dipoles, P and M, it works only if the distance between P and M divided by C, where C is the celerity of your electromagnetic wave, is greatly inferior to the wavelength divided by the same C. Yeah. So we can ask ourselves, well, maybe we can define other RQS that will help us to solve many systems. So there is another one called the magnetic RQS. Basically, you'll say that the time of your study is inferior to the time of propagation of the magnetic. Uh, you say that the effects of currents are greatly over the effects of the charges. So you can in this you can remove this, if I'm not saying bullshit. Yes, it's not bullshit. Okay, so you are removing this part because you are saying that it doesn't like really care by hypothesis, and you obviously conserve this because the magnetic field has nothing to do with the hypothesis, and this one is okay. And you can pretty much rewrite it by doing a combination of this but it's kind of boring with the gradient, the Laplacian of V, where V is the potential of the electrostatic potential. And as for energy electromagnetic, essentially in a magnetic form, meaning that B squared divided by 2 mu 0 is greatly over epsilon 0 E squared divided by 2, which is at the first part um, um, the energy given by magnetic, and at the other part the energy in how to say it, from electrostatic. So you'll say that magnetic electricity is greatly over electrostatic energy. We can notice that it's greatly used in phenomena of induction from studied by Neumann. And for example, that's what you use in induction thingy on the kitchen, because it's the magnetic energy that will matter. Then you can define another RQS, an electric one that will be basically okay, I'm removing that. That will basically be the reversal. You'll say that yeah, the electric field E has almost the same characteristic as the electrostatic field, which means that its rotational is 0. So yes, I'm not saying bullshit. This is 0. And then you can rewrite obviously E with the Laplacian of V, because E equals minus Laplacian of V, where V is the potential electrostatic, the electrostatic potential. Obviously Maxwell ampere, this one will get this term out and you will get this one. Okay, so the condition of validity of this is obviously the reversal, because you'll have electricity that matters more than magnetic field. So it's just the same thing. Epsilon 0 E squared divided by 2 is superior to B squared divided by 2 mu 0. And this illustrates the notion of capacity of a capacitor that can be extended from static to different regimes. So yeah, this is very used in physics because you'll often do the hypothesis that your object doesn't have um, some energy that matters. Like you say, this is too small, I don't care, and that will be it. Okay, so thanks for watching, and bye.